Okay, here we are at the Albuquerque Open Space Visitor Center, and we are going to be participating in Cosmic Carnival and presenting. In this case, we try to describe what a black hole is and where we find black holes and why black holes exist. And I have a small demonstration here showing the philosophy, the physics, a little bit of the physics behind what a black hole is. You can see many YouTube demonstrations of black holes and explanations of black holes on the internet. So you're stuck with me this time. Actually, a black hole is the end point in the life of a particular type of star. You've probably all heard of white dwarfs.
Yes.
Or neutron stars.
Yes.
And we know our sun is a star. What's going to be the end point of our sun in another 5 billion years? Well, it's going to grow up to be a red giant. It's going to blast off the outer surfaces of its atmosphere, and it's going to produce a planetary nebula, and the central core will become a white dwarf. Mm-hmm. Our sun we call one solar mass because it's our sun. And other stars that may be slightly larger than our sun can still have a end result of a white dwarf. But the material that's left inside the core after the atmosphere is blown off can be no more massive than 1.4 solar masses. That's called Chandrasekhar limit. So anything that's left that's bigger than 1.4 solar masses cannot become a white dwarf. What does it become? It becomes a neutron star. The center of the star crushes down even further, and the center of the star becomes a neutron star. Well, neutron stars are very fine. We love them because they form pulsars. They have magnetic fields and they spin very rapidly, and they're very good clocks. And but a neutron star also has a limit. The material that's blown off from a star, if it results in a core that's larger than 3 solar masses, anywhere from 3 to 10 solar masses, cannot become a neutron star. It just gets totally crushed. And those are the end results that we call black holes. What is a black hole? A black hole is called a black hole because you can't see it. You can see a neutron star, you can see a white dwarf, you can see the sun, you can see red giants, you can see all kinds of stars, but you can't see a black hole. So how do we know they exist? Good question. We know a black hole exists because of the effect it has on the material and the stars around it. Okay, now let's assume that we have here these 2 models. This is a stretchy material, and we call it the fabric of space. It's really just a 3-dimensional model of what 4-dimensional space really is. We're talking about X, Y, and Z, and time. Those are 4 dimensions. But we can't really demonstrate 4 dimensions. We have to demonstrate only in 2 dimensions. So this is a representation of what space is. And normally, an object moving in space, like this marble, this goes a straight line. Okay? You set it across space, and it follows a straight line. What happens if there is an object like the sun in the space?
It bends space.
No longer does the object go straight, it curves. I should have you do this. See if you can do it without throwing the marble off the...
I'll attempt it.
Okay, don't, you can use one of those marbles. Don't bounce it, just roll it. Yeah, so,
okay.
so a mass, what's mass? Any idea what mass is?
It's molecules and atoms that actually have density.
It's a amount of material,
Okay.
right? Could be molecules, could be atoms, anything that we can touch and hold, and
Right.
even though you wouldn't want to touch them.
No.
Okay, it's mass. And so if this is the sun, this has a mass of 1 solar mass. And you can see when you put it on our model space, it bends space.
Right.
It curves space. And so the objects which are coming close to the sun, their trajectory is bent.
Right.
Even if the object is only a lighter, is light. The object, the trajectory is no longer straight. It's bent. Slight
Right.
curvature. And we know this happens. This is what Einstein predicted in his general theory of relativity, that even light traveling at 186,000 miles per second, when it comes close to the sun, its trajectory will be bent, slightly bent. And how do we know that? Because back in, I don't know when, 19 something or other, there was an eclipse of the sun, and they had photographed the area where the sun was going to be, the star field,
Right.
before the eclipse, several months before the eclipse, to see the exact positions of all the stars. And then when the sun was in that field, and the moon, normally when the sun is in that field, you can't photograph anything,
Right,
it's too
right.
bright. But when the moon covered the sun, and they photographed the field again, then the stars that were closest to the sun had shifted in position slightly. So the light that's coming from those stars was actually bent. We call that gravitational bending of light. And now, for even more massive objects like galaxies or clusters of galaxies where you have extremely large mass, let's say thousands and thousands of times the mass of our sun, the light that comes close is shifted, its gravitational redshift. It's called gravitational lensing. Okay?
Okay.
A galaxy that's behind a very massive object whose light shines through will not come straight at you. It will come on both sides of the object and get bent around. So you see two objects.
Like going around the Milky Way.
Sort of, yeah. Okay. Now, I forgot to mention that black holes come in several different varieties. They can be stellar black holes, like a very massive star. That's when it explodes and gives off mass so that it's at least greater than 3 solar masses. But it could be up to 10 or 20 or 30 or 50 solar masses, because there are some very big stars out there. Though the endpoints of those stellar lives are a stellar black hole. But you can also have black holes at the center of our of a galaxy. If we take a look at this poster over here, you can see here there's some of the conditions I was explaining before. If you have a star like our sun, it is created in a star-forming nebula. Here's a sun-like star, and here's a very massive star.
Wow.
Our sun goes into becoming a red giant, a planetary nebula, and a white dwarf. Massive stars, more massive than the sun, red supergiant, they explode in a supernova. They can be a neutron star, if the resulting mass is less than 3, or a black hole. And then the material that's given off in the planetary nebula and in the supernova remnant goes into forming more stars in the future.
Wow.
You've heard about we're all made of star stuff? All the elements that are generated during the life of the sun and the life of a massive star, like sodium and
Right, all the elements.
nitrogen and everything, more massive than hydrogen and helium, enters the interstellar space again, and so future generations of stars have metals. And we get formed out of
The birthplace of stars.
right. Okay. But what happens when you have many black holes near the center, stellar black holes, near the center of a galaxy like our Milky Way? Our Milky Way has over a couple hundred billion stars in it,
Right?
like our sun. And the concentration is very large near the center. For example, here we have a typical galaxy. There's another, the Andromeda galaxy. These galaxies you see look similar to our Milky Way galaxy with spiral arms,
Right.
but a very dense concentration of stars in the center. So you'd imagine that over the lifetime of the galaxy, many stars, many massive stars, have evolved and created black holes, and these black holes are in the center, are
Within
much
our
more
galaxy.
concentrated in the center of our galaxy than
gosh.
near the edges. And they sometimes merge together, and now we know that actually our galaxy has a massive 4 million solar mass object at the center.
Oh my gosh.
4 million solar masses, and that's a small one. There are some galaxies, I can't say exactly which one, but there are other galaxies, like here's the Sombrero galaxy. Here's an elliptical galaxy. They may have black holes in their center. We call them supermassive black holes that are more massive than several billion solar masses. So it may interest you to know that the most recent Nobel Prize in physics, are you aware, it was given to researchers, to astronomers, for their 20-year research on the black hole, the center of our Milky Way galaxy.
Oh my gosh.
Yeah, they are the ones that determined what the mass is of our galaxy, of our solar mass, of the supermassive black hole in the center of our galaxy. And how did they do that? Well, it turns out that, like I said, the only reason we know that an object like a black hole exists is the effect that it has on its surrounding material. So using infrared radiation, where you could penetrate all the way to the center of our galaxy, it's like, say, here, we're out here, and you look toward the center, and when we look toward the center, you see lots and lots of stars and lots and lots of dark nebulae and so on. You can't really see all the way to the center. But using infrared light, they're able to look all the way to the center and identify several stars very close to the center that are actually orbiting the center. They're so close to the center that they orbit in periods of only 20 or 30 years. And over the course of that short amount of time, since the 1990s, they're able to follow the orbits of these objects, and then using Newtonian physics and the laws of gravitation, they could determine what the mass is of the central object that causes these stars to orbit the way they do. And they determined that the mass was 4 million solar masses, and it's in such a small area that you can't really expect it to be anything other than a black hole, supermassive black hole. So now we have, black holes and gravity and the curvature of space are all interrelated. This we call the fabric of space, and we showed that with a massive object, such as this one, space really curves.
Right.
With a lighter object, like this, it doesn't curve quite so much.
But basically, any object in space is going to cause a curve.
Any object in space curves space.
Right. Okay.
But
got it.
the mass, a mass like you and I, or the Earth even, it's such a small mass that the curvature is almost unnoticeable. Although it is important for GPS.
Oh.
Yeah, you got to know
Oh,
where
yeah.
those satellites are. And because of the difference in time caused by gravitation and the difference in the direction of the radiation that comes. So what would happen if we had a sun in the center here? Okay? And our Earth, let's say here's our Earth, our orbit's this. Curvature of space causes our planet, the Earth, to orbit the sun.
Right.
Okay? Gravity of the sun is caused by the curvature of space. If the sun were not there, space wouldn't be curved, and the Earth would just go straight. Okay?
Wow.
So the more massive the object, the more space is curved. And the orbits, what happens is our Earth goes round and round and round in the orbit. In this demonstration, the Earth eventually ends up falling right to the center because of the friction with the fabric here. But normally in space, it's empty. There's no fabric, so it just keeps going round and round and round and round. It's like a satellite above the Earth. Just keeps going round and round and round. But gradually, its friction with the upper atmosphere will cause it to fall to the Earth. That's why satellites have limited lifetimes. Right. So here we have a black hole that is the curvature. The space is so curved. There's so much mass in a very, very small region of space. And a black hole is black because even light is not traveling fast enough to escape a black hole. And we all know that nothing can go faster than the speed of light. And the speed of light is 300,000 kilometers per second, 186 miles per second. It goes around if light could go around the Earth in curved lines, it goes 7 times around the Earth in 1 second. It takes 2.5 seconds for light to go from us to the moon and back. That's why there's a delay in our radio communications with satellites and space probes. So black hole curves space so much you can see it out here. Space is, if we get further and further away from the black hole, if this thing was big enough, space would be relatively flat.
Right.
Okay, and because the curvature gets steeper and steeper and steeper, the curvature is somewhat. There is a little curvature out here. Gravity, we call it gravity, is caused by the curvature of space. Gravity extends forever, out infinite. Gravitational effect on the body is extremely small because it's a 1 over r squared.
Wow. Yeah.
So the larger r is, the lower and lower gravity is by the square. The further and further we get away. But very close to the object, then the space curves stronger and stronger and stronger. So gravity gets stronger and stronger and stronger. And it's so strong that even light cannot escape. By the way, here's an illustration of our galaxy. This is our Milky Way galaxy. My attempt to show where our sun is, where the spiral arms are, where the black hole, the supermassive black hole is in the center. And most people are unaware, actually, that our galaxy is not circular in the center. There's a bar.
Right. Well, galaxies have different shapes.
Galaxies have different shapes. Some have bars and some do not. And it's very difficult for us because we're in the galaxy. We're in the plane of the galaxy. And so for us to look toward the center and see a bar can't be done. Very difficult. It's too much junk. Like we can't see the black hole, we can't see the bar. But you look to the side and statistically that's a subject for another lecture. So black holes just keep getting bigger and bigger and bigger. The black hole in the center of our galaxy is probably accumulating mass as we speak. Because, like I said, stellar black holes in the center, where they gradually end up right in the center and they merge in the center. And black hole in the center can't be seen because light can't escape, but it captures all objects that come closer than what we call the event horizon. The event horizon is also called the short shield radius. It's actually a measure of the radius or the size of a black hole, which if you get closer than that size, you can't escape. Even light can't escape.
Okay.
And the more mass is, the bigger and bigger is the short-scale radius. If our Earth, or if the Sun, let's see if I get this right. If our Earth were to be squished down into a black hole, which it can't, remember I
Good
said
to know,
it has
yes.
to be at least more than 3 solar masses in size, in mass.
Right.
But if we could squish our Earth down to the size of a black hole, it'd be about 1 inch in diameter. 1 inch in diameter. And the Sun would be, you know, a few meters in size. But you can't make a black hole out of our Sun, and you can't make a black hole out of us or the Earth. But
Good.
extremely massive stars, you can make a black hole, and in the center of our galaxy, then there are many, many extremely massive stars that have merged in the center. Now we have 4 million solar masses. I don't know, in another few billion years, we may be the size of several billion solar masses in the center of our galaxy.
So how does that relate to something I read that said the galaxy is expanding?
The galaxy or the universe?
Yes, good point, isn't it? The universe is expanding. But wouldn't that also mean if the universe expands that the galaxies are expanding or not?
Sure. Space is expanding.
Right.
Space is expanding. So objects in the space are also
Yes, expanding.
But our galaxy, the Milky Way galaxy, is about, let's see, the center of our Milky Way galaxy is about 26,000 light years from us,
Yes.
from the sun, 26,000 light years. Okay, it takes 8 minutes for light to come from the sun to the Earth.
Right.
For light to go from the sun to the center of our galaxy, it takes 26,000 years.
Oh,
Okay. Where was I going with this? Size of our Milky Way galaxy. Our galaxy has another neighbor we call the Andromeda Galaxy,
Right.
which actually turns out to be bigger than, as far as we know, than our Milky Way galaxy. Like I say, it's hard for us to measure our Milky Way galaxy because we're actually in it.
right.
It's
right.
like being one tree in the forest, you don't know how big the forest is. But astronomers have kind of figured out over the years that the Andromeda Galaxy is larger than the Milky Way Galaxy, and it's 2 million light years away. Okay, how much bigger is that than the distance between our sun and the center of our galaxy? And there are other galaxies in our neighborhood, not as big as the Andromeda Galaxy, dwarf galaxies. There's about 30 or 40 in what we call our local group. The 2 closest of those are called the Magellanic Clouds. We have the large Magellanic Cloud and the small Magellanic Cloud,
Right.
and they were first discovered by
Magellan?
Magellan.
I always mispronounce them because I used his
Magellan.
name.
And they're only observable in the southern hemisphere. If you get
Oh.
down to maybe the tip of Florida or the tip of Texas, you can see them occasionally. Okay, now the point being that our neighborhood, our galactic neighborhood, is populated with other galaxies, and they are moving in space. They all have gravity. They are attracted to one another. They all orbit a common center of mass, and eventually they'll merge. In another, I don't know how many, 4, 5 billion years, who knows? We had a lecture on it in one of our meetings. It showed eventually the Milky Way galaxy and the Andromeda galaxy will merge. There's evidence that the Magellanic Clouds have actually started to merge with our galaxy. There's trailing stars and so on, and hydrogen atoms. Yeah, so, you know, it's not all tranquil. It's not all calm. So eventually the black holes in 2 galaxies may merge. There are actually a couple galaxies, I can't remember the name of them, but that have been detected to have 2 nuclei.
Oh my gosh.
2 supermassive black holes, probably the result of a merger of galaxies. So now you think you know a little bit about black holes? I don't claim to know very much about black holes.
Wow.
Black hole is really just a singularity in space. It's something that we'll never know what goes on in the center because we can never see there, and we can never observe any object that's actually come from there because nothing comes out.
Right.
It all goes in.
So the key element to remember is stay away.
Yes, and watch the object to go around a black hole eventually. Now, have you seen these devices sometimes in shopping malls where you put a penny and it spirals around like that?
Yeah.
You show it spiral around. Eventually ends up right in the center. And all sorts of interesting things go on that if you were to come into a black hole, actually go inside the Schwarzschild radius or the event horizon, time would slow down.
Oh.
Time would slow down, and tidal disruption would stretch you out into a long spaghetti thing. You wouldn't be able to experience the experience because it would completely stretch you out, and the clock that we see, your clock, would go slower and slower, and the light, as you get closer and closer to the center, would become redder and redder, become gravitationally redshifted.
Oh.
But anyway, don't worry about the sun becoming a black hole. And don't worry about the sun dying because it's already lived about 5 billion years. It's got another 4 or 5 billion years to go before it becomes a red giant, gives off its atmosphere, becomes a planetary nebula, becomes a white dwarf. And once it's a white dwarf, it'll last forever. It's just like an ember, an ash, slowly cooling off.
Wow.
Okay.
This is great. Not great to be too close, but wow. It actually slows time down. So the concept of time as the other dimension is really quite accurate.
Yes, that's one of the reasons why we have to take account of that for the GPS satellites.
Right.
And not only the gravitational redshift, but the time dilation. And this was all part of Einstein's theory.
That's
Forgot to use the baseball.
fascinating.
Forgot to use the baseball. It's not the size, the physical size. This one weighs about the same as.
Oh.
Let's see, this one. Yeah, it's not the physical size.
It's the density, right?
It's the density. It's the amount of material and the distance you are away that curves the space. See, the space curvature out here is about the same. It's not very much curved out here, and it curves more and more as you get closer. Same thing here. So it's not the size of the object; it's the mass and density, mass of the object, and the distance you are from it that causes the curvature of space.
So Pluto would curve space more than one of our gas giants, right? Or not?
No, it's the mass. It's the mass. It's the mass. You can crunch this down into something like this,
that.
and it still curves space the same. If these two weigh the same. This is supposed to weigh about the same as this.
Okay.
It's supposed to be a softball.
Oh.
No, I didn't have a softball.
Oh.
So we got a hard ball, and we got this.
But it's still, yeah.
And this is more dense, this is less dense.
Right.
But the total mass is about the same. And if you're out here, you wouldn't know whether you were orbiting that or
that.
orbiting this.
Okay.
And people say, what would happen if the sun were suddenly to be replaced by a black hole?
Well.
It'd be the same mass. You can't do it
Right.
because it's not the correct mass, but it would be the same mass. It'd just be a lot smaller, and it would curve space the same, and we'd continue to orbit just like we're orbiting now.
Okay.
The only problem was we wouldn't have the light and the heat and the energy from the
Right.
sun. So life wouldn't exist as we know it on the Earth. But we'd still be orbiting merrily away. Whether or not our orbit was almost circular like the Earth's orbit, or elliptical, almost elliptical, or very elliptical like some cometary orbits, or parabolic or hyperbolic. I mean, the sun is there, it curves space, and that's what causes the orbits. We can go on and on.